Hi guys, welcome back to my mathematics tutorial. My name is Peter C. Dogbo Jr., the mathematics tutor and instructor of mathematics at the University of Liberia. In my today's lecture, I will be looking at differential equations, and under differential equations, I'll be solving problems involving variable, separable, type 2. So in type 1 of variable separable, we discuss problems where we can easily separate the variables. That is, whenever a differential equation is given to you, you look at the problem and you try as to whether you can separate the variables. That is, all x on one side, or y on one side, if you are dealing with x and y. If that is possible, then it means that you can apply variable separable method to find a general solution by just integrating both sides of the equation. But some problems appear different. Now, some problems appear in a way that when you see the problem, the differential equations, you cannot directly apply variable separable. But when you apply some substitution, you find some derivatives, and then you put those substitution back in the problem, in the original differential equation, you can be able to separate the variables. So those types of problems are what we refer to as reducible to variable separable. So that is type 2 of variable separable method. So we want to look at additional problems. In the previous lesson, we did a lot of problems, so you can watch those lessons as well if you need to. So let's look at this problem. We have question 35 says cos of x plus y dy equals to dx. So if this angle had x plus 1, it means within here we just have a single variable, which is x. So we can just divide both sides by cos of x plus 1. But since this now has y, this means that we cannot determine whether we should maintain cos of x plus y on this side of the equation or divide it by both sides, because there are two variables right here. So based upon that, we think of a substitution for these two variables right here, so that if we allow some variable to be equal to x plus y, if we differentiate, one of the variables will disappear. So we say let x plus y equals to u. Now we differentiate both sides. The derivative of u, since u is a function and y is a function, x is a variable within the functions. So we can have du by dx is just equals to 1 plus derivative of y is also 1, but we attach dy by dx since it is the name of a function. So we've gotten u and we differentiated u. So the next thing we need to do is to solve for dy by dx. So from this original equation, we can solve for dy by dx by just dividing both sides by by dx. So we can have dy by dx. So therefore, we will have cos of x plus y dy by dx is equals to 1. So this now becomes a rearranged new equation, old equation. So we substitute dy by dx within this. So we first solve for dy by dx here. We have dy by dx, or du by dx, minus 1 is equals dy by dx. Okay. So we go back to the original equation. This is the original equation. So we have cos of x now is just u times dy by dx is du minus, or du by dx minus 1, or equals to what? 1. So this cos of u dy by dx is just this, minus 1. Then we multiply. So it's cos of u du by dx, cos of 1 So cos of u times 1 is just minus cos of u equals to 1. Now I want to get rid of this dx, so we can multiply this whole thing by dx. So now we will have the x times this is just cos of u du. The x times this is cos of u dx, and then the x times this is dx. So we can now separate the variables. So we have cos of u du equals, now we send this one across. So if we send it across, it becomes positive. Then we can now factor out the x, because the x will be common to the two of them. So here will just be cos of u plus 1. Now, this is dx. So every other expression here must be in x. Since this is cos of u, we must divide it on both sides. So we have cos of u plus 1 divided by cos of u plus 1. So cos of u and cos of u will go out. We have cos of u du all over. Now cos of u plus 1 is the same as saying, cos of u 1 plus cos of u, whatever the case might be. So 1 plus cos of u all equals to dx. So because the variables now have been separated, we can now integrate both sides. Now, so this is where now we have to pay attention. So to integrate the first one, cos of u du all over 1 plus cos of u, we can consider this being like x all over 1 plus x. Wherein, since you have linear factors, you can apply long division. So you will apply long division here first. And then when you get that factor now, then you simplify. But there's a trigonometric case. So we don't want to apply that method, long division, and then so we want to apply some tricks. So what's a trick? We use a trick in previous lessons. Cos of u du. Now down here is 1 plus u. So we can say 1 plus cos of u, because it's the same thing in the denominator, 1 plus cos of u. Then we can just say minus 1. Because what? We added 1, because this one was a new thing we added to the problem. So we can just add 1 and subtract 1. Du equals to dx, the integral of dx. So you see, with that, we didn't change the problem is still the same. So our objective, yes, is to be able to integrate this problem in the best way we can. So 1 plus cos of u, 1 plus cos of u divided by 1 plus cos of u du. So you see, we're paying it, right? Minus the integral of 1 all over 1 plus cos of u du. But in our previous lesson, in lesson 30, in lesson 30, 34 or 33 or 32, one of them, we discussed, or we solved the integral of 1 all over 1 plus cos of u. We solved this by using the half angle identity. So we replace this 1 with cos square u over x, or u over 2, plus sin square u over 2. And we also brought in cos of u, which is cos square u over 2 minus sin square u over 2. So we use this also. Sin and sin will cancel. Sin and sin will cancel. You'll be left with 2 cos square u over 2. So 1 divided by 2 cos square u over 2. 1 over cos is secant. So this is the integral of secant square u over 2. So the integral of secant square is just equal to tangent. So this guy gave us tangent of u. So the integral of this is just tangent of u. So similarly, we can apply that same thing here, right? Now, what's about this? So if you didn't understand what I just did, we can do it together. I don't mind. So now what I did was I said note that from the Pythagorean identity that states that cos square u plus sin square u equals to this one. If we divide all of the angles by 2, we will have 1 equals to cos square u over 2 plus sin square u over 2. So this is the first one. So when I see 1, I'm going to replace it with that expression. The next one, cos of u. I know that cos of 2u equals to cos square u minus sin square u. So whatever I divide each angle by 2, so cos of u equals to cos square u over 2 minus sin square u over 2. So I can use these two identities to replace that. Thus, now the integral of this will just be du minus the integral of this one would be 1 all over. So the first one now is cos square u over 2 plus sin square u over 2. And then this cos of u will now be cos square u over 2 minus sin square u over 2. So what happens? You see that sin square u over 2 will cancel sin square u over 2. Now, remember you have on the right hand side the integral of the x, which is just x. So now the integral of u would just be u. Integral of du is just u minus. So we'll be left with 1 all over. Now cos square u over 2 plus cos square u over 2 gives us 2 cos square u over 2 du and then equals to x. That's what we got. Now 1 over cos is just equal to secant. So there is secant square u over 2 du all equals to x. So we know that the integral of secant square ax, for example, dx is just equal to 1 all over a tangent ax plus c. So with this property, we can now say 1 over 2. So the integral of this secant. So what is our a? A represents 1 over 2. So a is 1 over 2. So this now becomes, let's go. So the integral of this one now is 1 over a. So what is a? A is 1 over 2. 1 over 2. That's our a. Tangent of a again is 1 over 2 u. All equals to x plus some arbitrary constant c. So we just simplify now and bring in the value of u, and then we are done. So what was u? From the beginning, u was x plus y. So you got x plus y is our u. Minus, now this 2, if this 2 comes in the numerator, this 2 and this 2 will cancel. So we'll just be left with tangent of u all over 2 equals to x plus c. But what happens to x and x? X cancel this x. So y now can just be, if we send this tangent across, it will be positive tangent of, so this u again is x plus y all over 2 plus some arbitrary constant c. So this is the solution to the differential equation using type 2 of variable separable method that we call the reducible to variable separable. So thanks ever so much. Please don't forget to subscribe to our channel, like the videos, share them. Thank you.